Okay, so is it my imagination, or does it feel like everybody is relieved to be done with the, yeah? No, not relieved? I'm sorry? Oh, right, yeah, okay, that's small matter, yes, of course. Well, you'll get your grade back pretty soon, so, yes. Yes. Oh, yeah, so that's a very good point. So, um, if, did people feel it was challenging? More time, okay. A lot more? Okay. Um, was a little bit like life, right? Yeah. Okay. Okay. So, sorry. Let me just say something about that. It is the case that the class is, it's graded on a curve. So, in fact, if the midterm's challenging, what that means is that then it's sort of, it makes it easier for you if you're the kind who is careless, right? So if it's not challenging, then what it means is that you really cannot afford to get any question wrong because, they're all relatively, straightforward, and if it's challenging, what that means is that, you can afford to make mistakes as long as you manage to think your way through something. So these different types of midterms sort of help different students, and hopefully it all averages out in the end, and everybody gets to demonstrate sort of their understanding in their favorite midterm and so on. Yeah? Okay. All right, so where do we go from here? So here are two things I'm going to do today in class. So this lecture will be about tying up some loose ends about conditional probability. So what we'll talk about is independence and conditional independence, the chain rule, and then we'll talk about unions of events. And that's it as far as that chapter on conditional probability goes. And then for the last half an hour, hopefully, if we have time, we're going to go over, oh my God, okay, so we don't. Okay, so for the last half an hour, if, assuming we have that much time, we'll start on random variables. So by the way, how many of you already know about random variables? Oh, good. Okay, so please, shall we settle down? Can everyone please settle down? Okay, yeah, all right. Okay, so let me just say a little bit about random variables. Okay, so it's one of these things again, which is not inherently a difficult topic, but it's something that takes a bit of getting used to. And it's a definition that took a long time. It took many smart people a long time to come up with a definition. So even though at the end of the day, when you look at it and you understand it, you'll say, oh yeah, when you understand it, you'll probably say it's not that hard. It's pretty simple. But you really do have to understand the definition. And what makes it difficult is that there's the intuitive understanding of it, and then there's the formal understanding of it, right? If we get to the formal understanding too quickly, it's too confusing. So we'll start with an intuitive understanding and then get to a formal understanding. Okay, so that's what we'll do for the last half an hour of this class. But to begin with, we'll talk about independent events. And okay, so what we say is that two events A and B are independent if and only if probability of A intersect B equal to probability of A times probability of B. Right? Another way of saying this, essentially an equivalent way of saying it, except in the trivial case where probability of A or probability of B is 0, is probability of A given B is equal to probability of A. Okay, so these two are essentially equivalent definitions. You can either say this or you can say that. Okay, so I hope you can see that the second definition is what we would think of as the intuitive definition of independence, right? So if I tell you A happened, it doesn't tell you anything at all about whether B happened or not. Your probability of B, if I tell you B happened, it doesn't tell you anything at all about whether A happened or not. Because the probability of A remains unchanged after you learn that B actually happened. And the reason they're equivalent is probability of A given B is just probability of A intersect B divided by probability of B, which is just by independence. By this first definition, this is probability of A times probability of B over probability of B. And this is where this whole assumption comes in that A and B are, they shouldn't have 0 probability. As long as they don't, you can cancel and you can just say that's probability of A. So you can see that, this second definition follows from the first one, assuming that B is a non-trivial event, and same thing, you can actually derive the first one from the second one in the same way, and so they are completely equivalent definitions. Yeah? Okay, so now independence is something that we've been using a lot without actually saying it formally, right? So, for example, if you were flipping a coin and you wanted to know what's the probability that it'll come up heads given that the previous toss was heads. So you're tossing it twice. Suppose that the first toss was a heads. What's the chance it'll be heads again? 1/2. Right? That's how you actually see that the probability of 2 heads is 1/4, because we just said, well, they are independent. You get 50% heads for the first one, and then 50% even if you knew the first one was heads, right? So this is the intersection of 2 events. The first one says that the first coin toss was a heads. The second one says that the second coin toss was a heads, right? So this is probability. Okay, so probability of heads is the probability first toss is a heads intersect that the second toss is a heads. And that's just by independence probability first toss is a heads times the probability that the second toss is a heads, which is 1/2 times 1/2. Right, so this is something that we've all gone through before. Okay. So let's see other examples. So other examples we saw was, if you're tossing 2 dice, what's the chance that you'll get a certain combination? Well, that's just independence. Well, let's do some other examples. So what's the probability you get a heads given that the last 10 tosses were heads? Okay. It's still 1/2, right? Because the coin tosses are independent. Now, this is something that, by the way, that it's very hard for humans to actually understand this intuitively. So, you can do this experiment where you ask people to generate a random sequence of heads and tails, or zeros and ones. Okay? And if you ask somebody to generate this for you, it turns out you can actually tell whether it was generated by a human or whether it was generated by the toss of a coin. Okay? And the reason you can tell, okay, you can actually write a simple computer program that will tell whether it was a human at the other end tossing the coins, or sort of thinking it in their heads, or whether they were actually tossing coins and entering that. And the reason you can tell is because this sort of a run of heads makes a human being very nervous. Right? So if you see 3 heads in a row, if it's a coin, it doesn't care whether the next one is going to be heads or tails. It just gives you 50% heads, 50% tails. Whereas when a human being generates it, they get very nervous after seeing 3 heads in a row, so they sort of put in a tails there. Right? And you can tell because the number of, the longest runs you get of heads or tails are much shorter when a human generates it than when they're generated by a fair coin. Okay, so these are all examples of independent events. So let's see what are other possible examples. So let's suppose that we were placing, we had n bins, k balls, and we place these k balls in the n bins. And suppose A is the event that the first bin is empty, and B is the event that the second bin is empty. Are these independent events? No. No? So how would you tell? So remember, there are 2 ways you can tell. You can either say, is the probability of A intersect B the probability of A times the probability of B? Or you could say equivalently, suppose you know that A was true. Does it make B more or less likely, or does it keep the probability exactly the same? So once you know that one of these events has happened, is it more likely that the second one would happen, or less likely that the second? Would it change the probability that the second one happens? So what do you think? What should be the case? Yes?
In an extreme case, one ball, it's 100% initial probability.
I'm sorry?
In an extreme case, one ball.
Yeah.
Then if A is empty, then if A is full, then there's zero chance that B is empty.
Oh, good. Yeah. So that's a good point. One way you can try to understand these sorts of things is look at extreme cases. So if there was only one ball, if you happen to know that the first bin was not empty, right, that completely tells you about the second bin, because there's no other balls to go in there, so it must be empty. Right? Yeah. Here's another extreme case. So suppose you had only 2 bins. Right? If you knew that the first bin was empty, you know for sure that the second one was not empty. Right? Yes? Well, let's see. What's the chance that the first bin would be empty? So what's the probability that the first bin is empty? Well, how many ways are there of placing these k balls in the n bins? There are n possibilities for the first one, n for the second, n for the third, n to the k. And how many ways are there of placing the balls in the bin so that the first bin is empty? N minus 1 to the k. So it's 1 minus 1 over n whole to the k. Okay, now suppose that you know, suppose that you knew that the second bin was empty. Now what's the chance that the first bin is also empty? Well, how many ways are there of placing the balls now? N minus 1 to the k, right? Because the second bin is empty. There are only n minus 1 other bins that the balls can go in. So the first one can be placed in n minus 1 bins, which is all except this one. The second ball can be placed in n minus 1 bins, which is all but this one, and so on. So there are n minus 1 to the k ways of placing the balls. Right? Out of these, how many ways are there of placing the balls so that the first bin is also empty? N minus 2 to the k. Okay. It turns out that the second probability, this number is smaller than that one. Yeah? Okay, so conditioned on knowing that one of the bins is empty, the chance that another bin is empty it actually goes down, right? Because you have to sort of put the balls in fewer bins, and there's less chance that you can get an empty one. Okay, so maybe, oh shucks. Okay, sorry. Okay, so should we do another example? What about, what's the probability if you draw two cards? What's the probability that the second card is a spades, given that the first one is a spade? Are these two events independent? If you're drawing two cards and you want to know, if the first one is a spade or the second one is a spade, are these independent? Right? I'm sorry? No, you're not replacing the cards. So let's say you're getting a bridge hand or something. You saw the first card; it was a spade. And now you pick up the second one. Should you expect it to be a spade with equal probability? Right? Because for the first card, it was 1 in 4. Right? But given that it was a spade, the chance that the second card is a spade is now much smaller. Because there are only 12 ways of getting a spade, and there are 51 cards. So it's a smaller probability. So these are not independent events. Right? So this is, this notion of independence is a very fundamental notion in probability. It's worth understanding it intuitively, right? To understand, because whenever you have independence, it completely simplifies probability calculations. But on the other hand, a great source of errors in probability is when you assume something is independent and actually it's not. So, okay. Now what? Now underneath this. Okay, so okay, so now here's another version of this this rule about conditional probability. What it says is it's what's called the product rule. What it says is the probability of A intersect B is the probability of A times the probability of B given that A occurred. Right? So if you want to know what's the chance that A and B both occurred, you first figure out what's the chance that A occurred, And then you figure out what's the chance that B occurred given that A already occurred. Okay? So, and a generalization of this is what's called the chain rule. So this is called the chain rule. And what it says is, suppose you have a number of events, n events, and you want to know what's the chance all of them occurred. Then that's the same as the probability that the first one occurred times the probability that the second one occurred given that the first occurred, and so on. The probability that the third occurred given that the first two occurred, and so on. Okay, so where do we apply this kind of chain rule? So I claim we apply it all the time. So for example, if you wanted to know what's the probability you get, of a heads, tails, heads, heads, where the probability of heads was P and the probability of tails was Q. Well, you could write this as P times Q times P squared, right, which is P cubed times Q, because you say, well, it's the probability that heads occurred times the probability that tails occurred given that heads already occurred times the probability heads occurred given that head, tails occurred, etc. And then you use the fact that it's all independent. Right? Let's do another example. So let's say that you had a poker hand. And you want to know what's the chance that it's a flush. A flush means all the 5 cards had the same color. Right? Well, so you can again do this by the chain rule. You could do it by counting, but you can also do it by the chain rule. So the way you say it is, well, let's draw the cards one at a time. Now the first card, it doesn't matter which one you drew. Right? So A1 is just anything. It's the entire, it doesn't matter which card you drew, you're still okay for a flush. Right? What about A2? What's the A2? What's A2? Okay, so whatever the suit was of the first one, that's what we're asking for. Okay, so maybe we should do it slightly differently, and let's just to make it clearer, let's say that A1 was the event that you got one of the spades. Right? A2 is also an event that you got one of the spades. And A5 is also an event that you got one of the spades. So in the first draw, you got the first card was a spades, the second card was a spade, up to the 5th card. Right? You know what I mean by this. So, okay, sorry, I shouldn't have written it like this. Let me write it like this instead, just to be clearer. So let's say S is the set of all spades. So it's the 13 cards that are all spades. Okay? So what we're asking is, what's the chance that all 5 cards that we drew were spades? So we are interested in the probability A1 intersect A2 intersect A5. Okay? And so what's this probability? Well, it's the probability of A1, which is 1 over 4. Right? There are 13 over 52. Times the probability of A2 given A1. Times the probability of A3 given A1, A2, etc. So what's that? Well, this was 1 over 4. Now, given that A1 was already a spade, what's the chance that A2 is a spade? Right? So we've already drawn one hand and it turned out to be a spade. What's the chance that the second card is also a spade? So now what's left is a deck of only 51 cards. And out of those 51 cards, we know that there are only 12 spades left. Right? So the chance is 12 over 51. Okay, so maybe it would be easier if I wrote this first thing as 13 over 52 times times 12 over 51. And then the probability that A3 is a spades given A1 and A2 were both spades, that the third thing is a spade given that the first two cards were spades is 11 over 50 times 10 over 49 times 9 over 48. Okay? So this is a chance of drawing a flush which consists of all spades. But then there's a similar chance of drawing a flush which is all hearts, etc. And so the probability of a flush is just 4 times this. Okay? So I claim that this is a rule that you've probably already used, some of you have already used, and what we are doing here is we are just formalizing it and saying, this is a way that you can always think if you want, where when you're making a bunch of choices, you just think of them as a sequence of choices where the probability of this sequence of choices is the probability of the product of the probability that you'll make the next choice correctly, given that you made all the previous choices correctly. Okay? Let's see. Any questions? Should we take a 1-minute break? Let's see. Are we on to the next? Yeah, we're on to the next. Okay. Okay. So here's what we're going to do next. Okay, so next we're going to talk about one more idea which has to do with what's called the union bound. Okay, so the union bound is one of the most, it's a very simple way of providing a bound on a probability without calculating it exactly. Okay, and it turns out that when events that you're thinking about get sufficiently complex, then it's very hard to compute probabilities exactly. But if you get a very good bound on it, if you can say, Well, you know, I can't compute this probability exactly, but what I can do is I can tell you that you know, it's at least this much, or it's at most this much. And I'm pretty sure that I didn't make a very big error in my estimate. That's usually good enough for most purposes. And this union bound is one, you know, it's one of the simplest and the most applicable ways of doing this, of estimating probabilities. So before I talk about the union bound, let me talk about disjoint events. So this is something we talked about last week. So let's say that you have a bunch of events, A1, A2, A3, up to AN. Okay? So you have a bunch of events, A1 through AN. And let's say that A is the union of these. So A is this event. Right? A happens to be the union of A1, A2, etc. So then, if you want to know what's the probability of A, one thing you can always do is you can say, well, if I can compute the probability of A1 through AN, then I can compute the probability of A, because it's just the sum of the probabilities of these disjoint sets. Right? So for this to happen, it's essential that these sets are disjoint. Right? Okay, now, so what happens if they're not disjoint? So that's the case where we talk about the union bound. So in the case of the union bound, this is our picture. So there's our sample space. That's A1. That might be A2. A3, we don't know. Maybe it's like this. That's A3. A4 is that one. That's A5. Well, A5 might be that set, and so on. And that's, suppose A is A1 union A2 union A5. Right? It's the union of all those. So A is this event. Right? So now, what we can say is that the probability of A is at most the probability of A1 plus probability of A2 plus probability of A3 plus probability of A4 plus the probability of A5. Does everyone see this? Does everyone see why this is true? Right, so if they were disjoint, then you could add the probabilities. If they intersect, then when you add the probabilities, you're overestimating the probability. But that's okay, as long as, if the intersections are small, then it doesn't matter. Maybe you haven't overestimated by very much. But no matter what, you always have this inequality. And that's the union bound. Right? It's a quick and dirty way of estimating the probability, of bounding it, saying it's not bigger than this much. Okay? So, does anybody not see why this is true? Everybody see it? Really? Okay, so how would you prove it? Let's take a minute and just think about how you'd prove that this is true. Let's just say that you had two events, right? So this is your picture. That's omega, that's A1, that's A2. How would you prove that the probability of A1 union A2 is at most the probability of A1 plus the probability of A2? Yeah, just think about it for 30 seconds or a minute. Sorry, was it a clarifying question or an answer? Yeah? Okay. Yes. I'm sorry? Are you, okay. All right, give everybody just 15 more seconds and then. Okay, so, yes? Yes. Yeah. Yeah. Good. Very, very good. Yeah. Okay, so let me try to summarize. So the key point to remember is that the probability of an event. Remember, what's a sample space it consists of a bunch of sample points, right? So you have a bunch of sample points, which we call omega sub I or whatever. They're sample points, and then what's the probability of an event? It's just the sum over all the sample points in the, it's the sum of the probabilities of all the points which fall within this event. So if you're looking at the probability of A1 union A2, you have to look at all the points which fall anywhere inside A1 union A2, and you have to add up those probabilities, right? But then if you were to add up everything inside A1 and everything inside A2, you're certainly getting everything inside A1 union A2. Some points you're counting twice, like the ones in here. But that's okay. That's why it's an overestimate. Right? That's the whole point about the union band. Okay, so now let's use this to do something. Okay, so let's say that you had a hash table. And the hash table has n entries in it. Okay, it's a table of size n. And each time you place an entry into this hash table, it's placed randomly, right? So every time you have an entry, it just goes into a random entry in that hash table, okay, in a random location in the hash table. So the question is, how many items can you place in the hash table before you expect to see a collision? Before you would get a collision, let's say with probability half, right? Or how much can you load up the hash table with a pretty good, where you can be pretty confident you won't see a collision, right? You have a collision whenever two items hash to the same value, to the same entry, right? Okay. So it turns out, what's this problem? Well, let's say that the number of items was k, then this is really the same thing as a question about if you're placing k balls in n bins, what's the chance that no two balls ended up in the same bin, right? That they're all in distinct bins. Now that's not an easy question to answer exactly. I mean, we can do it. You'll have to do various calculations, approximations, and so on. But then, if you want to just know approximately what the answer is, you can figure it out quite easily using the union band. Yeah.
Quick clarification. Are we asking what's the probability that the next ball we add will collide, or the probability that there's already been a collision?
The probability that there's a collision anywhere, right? By the way, this should remind you of something that we've already discussed. The birthday paradox. So we're asking, how small should the, if you're asking a group of people for their birthdays and you want to know what's the chance that two of them had the same birthday, how small a group should you select so that you're pretty confident that there won't be a collision? And remember we said roughly, you know, if there were n days in a year, then roughly at square root n you already get a collision. What we want to show is that as long as the number of people was much less than square root n, the chance that you get a collision the same birthday is very small. Okay? So that's what we're asking here. And we want to do this without computing all kinds of factorials and so on and having to calculate, approximate, whatever. Right? So how do you do this? Well, the answer is to use the union bound. So let A be the event that there's no collision. Okay? So what we want, and let B be the event that there is a collision. So what we want to figure out is we want probability of A is large, or that the probability of B is small. Right? So what we are going to do is we are going to express B as a union of events, and then show by the union bound that B is unlikely to happen. Okay? So what's B the union of? So B is the event that there's no collision at all. I'm sorry? Oh, sorry, B is the event that there's a collision. Sorry, B is the event that there's a collision. So we want to express it as a union of different events. So what would those events look like? It could be one collision, two collisions, and so on. What's another way of writing it as a union? Of something that's very simple and which we might have a hope of bounding, you know, writing down the probability of. Yes? Okay, it could be a collision in the first bin or the second bin or so on. Okay? That's a perfectly good way of writing it down. By the way, all these are good, you know, good things to think about. So B is a union of, for instance, that there's a collision in the first bin or there's a collision in the second bin and so on. Now the difficulty is how do you write out the probability of that? So you've got to, you know, we are trying to do two things. We are trying to write B as a union of different events, but we want to pick events so that we can actually write down the probability of the individual events. And then we'll add them up and use the union bound. So what is this? Can you think of a nice way of writing B as a union of different events? So here, maybe let me just tell you, okay? So B is going to be the union of events like this. If there's a collision, maybe there's a collision because balls 1 and 2 collided. Or maybe ball 1 and 3 collided. Or maybe ball 1 and K collided. And so on, up all the way through maybe ball K minus 1 and K collided. Sorry, is this? Okay, so the number of events that I'm writing down is every possible pairing, every possible pair of balls, which is how many? K choose 2, right? So there are K balls. There are exactly K choose 2 ways of writing this down. Now, okay, what's the probability of Bij? What's the probability that balls I and J collided? 1 over n squared. So let's see. Do you want to think about it for a minute? Actually, can we use one of the rules we already saw? Okay, so we want to figure out what's the probability that the ith ball and the jth ball collided, right? So how do we figure it out? We place the ith ball. Does it matter where we place it? No, right? So we place it, it goes into some bin. And now for the jth ball to collide with it, what must happen? It must go into the same bin. So what's the chance? 1 over n. Right? So that's why we pick these events. They are nice. You can write down their probability easily. So this probability is 1 over n. So now, what's the probability of B? So by the union bound, it's at most summation probability Bij for I over all ij between 1 and k. Yeah? Maybe assume I is less than or equal to j, so that you don't count the same pair twice. So you have k choose 2, so this is k choose 2 times 1 over n. Right? The probability of any one of them is 1 over n. There are k2 choose 2 of them, so there's, right? So as long as k times k minus 1 over 2n is small, then the probability of a collision is small. So for example, if you were happy with making sure that the chance of a collision is less than a half, you could choose k equal to square root of n. Right? Okay, so now it turns out this is a pretty good estimate. Especially when this number is small, when k is much smaller than square root n. This estimate, is very, very close to the true probability of this event. Even though we said it's an overestimate, right? The probability of B is less than or equal to this, but it actually tends to it. And the reason that it tends towards it, okay. So why does it tend towards it is because if you look at these Bij events, here's one of these, say B12, and then if you look at another of these events, say B23, it turns out that these events don't have much of an intersection. The intersection is very, very small. And so what you're losing by doing the union bound is not very big. Right? Because this event had probability 1 over n, this had probability 1 over n. And if you want to know what's the probability of the intersection, you can figure out that the highest it is when they had something in common. If this was 1, 2, this was 3, 4, then the intersection would be really tiny. But if you had something in common, then the probability of the intersection goes down like 1 over n squared. And so there's really not much chance of an intersection. And so that's why the union bound does well in this case. Okay, so let me just say this, and it's not something that we're going to be covering in any detail, but I hope you know there's something called the inclusion-exclusion formula, which goes like this. So suppose you have events A, B, and C. Okay, then you want to know what's A union B union C. This is the same thing as A union B union C. Oh, sorry. This is, it's not. What do I want to write? I want to write down, okay, so I want to write either the probability or the number of items in. So let me write it as probability. So it's the same as probability of A plus probability of B plus probability of C. But now what's happened? Well, we've counted this thing twice, we counted this thing twice, and we counted this thing twice. So we subtract it off. So we say minus probability of A intersect B minus probability of A intersect C minus probability of B intersects C. So we subtracted out this one, we subtracted out this one, we subtracted out this one. Okay? So what happened? Well, we got this right, we got this right, we got this right, but this one, what did we do with it? We added it how many times and we subtracted it how many times? Well, we added it 3 times when we took probability of A, B, C. Then we subtracted it 3 times, 1, 2, 3. So now we must add it back in. Right? So this is called the inclusion-exclusion formula. Right? In fact, it holds not just for 3, but for any number, for 4, 5, and so on, except each time you keep switching signs. You say probability of A union B union C union D is A plus B plus C plus D minus all the pairwise intersections plus all the triple-wise intersections minus the intersection of all 4. So as you keep increasing the number of sets, you just keep going, plus, minus, plus, minus, plus, minus, and so on. Okay? So, this is another way you can compute these probabilities exactly. We won't go into this in this particular class in any detail. Okay. Maybe we can take another 1-minute break, and then we'll start on random variables.
For the extra credit problem, do all the dice have to be positive? I'm aware I can just add any random number to this in order to make it.
Yeah, you can add something. You may as well make them positive. Okay. Okay, so shall we talk about random variables? Okay, so first of all, can anybody tell me what a variable is? What's a variable? Okay, so you probably learned about it a long time ago, and it's sort of basic to algebra. It took a long time to get at that definition. It's a symbol together with a set, or so for example, you might have a real variable, so you have a symbol, say x, and a set r, right? The reals, and you say, well, it can take on any value in that set. So now a random variable is a new way of asking a question about nature, let's say, about phenomena. So a random variable is a variable together with a probability that it takes on that value, each value. Okay, so for example, you might toss a coin, right? Now so your experiment might be you're going to toss a coin many, many, many times. And your random variable might be, how long do you have to wait before it comes up heads? Okay? So the answer is not one number. It's not, it's not 1 or 2 or 3 or 4, because it could be anything. But there's a chance that you'll see a heads. You'll only have to wait for 1 unit of time before you see a heads. There's a chance you might have to wait for 100 units of time before you see a heads. So each of these comes with a certain probability. And so a random variable is this. So for example, a random variable might be you repeatedly flip a coin, and you want to know, you might have a random variable called W1, which is the waiting time for the first heads. Okay. And so this random variable comes with, it can take on any non-negative or positive integer value. So the it can take on values 1, 2, 3, etc. And for each of these, you have a probability, right? So you have a probability p sub 1, p sub 2, p sub 3, etc. The probability that you have to wait that long for heads. Okay? So suppose, for example, that the probability of heads was equal to p, and the probability of tails was equal to q. Then what's the probability that W1 is equal to n? So if every time you flip the coin, it has probability exactly p of coming up heads and q of coming up tails, what's the chance that you have to wait for n steps before you get n flips before you get a heads? I'm sorry? Well, no, it's not a fair coin. That's the coin. It has probability of heads p and probability of tails q. 1 over p to the n. Well, you don't want that. You mean p to the n? P to the n. Well, I'm sorry? Yeah, so maybe let's try to think about what this event is. What is this event? What are the sample points here? What would it look like for the waiting time to be n? Yeah, it must be that you start tails, 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 and there are exactly n minus 1 of them, because otherwise you didn't need to wait for n steps. And then the last one must be heads. Right? So what's the chance of that? It's q to the n minus 1 times p. Right? Okay. By the way, these probabilities must add up to 1, right? Because eventually you will get a heads. So what does that tell us? summation n equal to 1 to infinity. Is it 1 to infinity? Of q to the n minus 1 times p is equal to 1. Okay. How do we know this is true? Well, you could either sum a geometric series, or you could say it's true because the probability is 1 that you'll see a heads at some point. Right? So it's a probabilistic proof of this statement. Right? Okay. Okay, so we can also generalize this, and we can say we have a random variable w sub k, which denotes the waiting time for the kth heads. So for example, w sub 2 says, how long do you have to wait before you see 2 heads? Right? W5 says, how many times do I have to wait before I see 5 heads? Right? How long would you expect W5 to be? How long would you expect before you see 5 heads? Maybe 10, right? Maybe you would expect to, if it was a fair coin, maybe you'd expect to flip it 10 times, something like that. But as a random variable, it's sort of telling us what's the chance that W5 equal to 10, what's the chance it's equal to 11, and so on. So let's see, what's the probability W sub k equal to n? So now how do we solve this? So what is this event? What do the sample points look like? The first thing you have to notice is that we toss the coin exactly n times, right? Because we are saying the waiting time is exactly m. So there are exactly n tosses. So there are exactly n of these. Now what must it look like? So what's the last toss look like? It's a heads. What about these previous ones? What do we know about them? So they're exactly k minus 1 heads here. Right? Okay. So now for any way of filling these in, what's the probability? So if the first k minus 1 were heads, and then we got tails, 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 and then we got a heads, what's the chance of that? Remember, each heads, the probability was p. So we have p to the, what is it? It's p to the k, q to the n minus k. That's for any one sequence. But now how many such sequences are there? Yeah, it's n minus 1, choose k minus 1. Right? Is everyone happy with that? Because there are n minus 1 positions other than the last one, and within that we have to distribute the k minus 1 heads. So there are n minus 1 choose k minus 1 ways of doing that, and for every way we do that, we get a sequence of exactly k heads and n minus k tails, which has probability p to the k times q to the n minus k, and so that's the probability. By the way, what does this tell us? We know that the waiting time for k heads must be something. So the summation over k of n minus 1 choose k minus 1, p to the k, q to the n minus k, k going from what to what? Oh, sorry, summation over n. N going from what to what? K to infinity is equal to what? Now you try proving that. Okay? So this is something that you should try to understand. Probability theory is a powerful way of looking at the world. right? It's powerful enough that we can prove things like this without even trying. Yeah?
Can you explain again why n minus 1 choose k minus 1 instead of n choose k?
Yeah, so there are n positions, but we know that the last one was a heads because we were waiting for that heads, right? So that last one is a heads. Now, how many positions do we have left? There are only n minus 1 left. And out of those, k minus 1 must be heads, right? Exactly k minus 1, and the rest must be tails because we were waiting for that kth heads. So how many ways are there of distributing the k minus 1 heads among the n minus 1 positions? It's exactly that much. Yeah? Okay. Okay, so now we get to the shocking definition of random variable. Okay, so you might think you understood random variables, but now we'll say what they are, and you won't understand what they are anymore. Okay, and then you'll go back and understand it intuitively, and you'll say, okay, it's a very simple concept. Why do they make it so difficult? And then you'll realize that it was a bunch of smart people who thought for a very long time before they came up with this definition, and it's the only right definition, and we are very grateful to them for coming up with it. But but why did they burden us with this? So let me tell you why they burdened us with this. So I actually learned probability theory from really he was a remarkable person. His name was Giancarlo Rota. He was a professor at MIT, and so he was one of the most prominent combinatorialists of his time. And one of the things he talked about was, he said, the purpose of this course, the course on probability that he was teaching, was to learn how to think probabilistically. And then he said, unfortunately, in order to learn how to think probabilistically, you have to learn the theorems of probability theory. Okay? But then, that's not what you're after. You're not after the theorems. You're after learning how to think probabilistically. And so he said, long after you learn the theorems of probability theory, the theorems will fade from your mind. And what you'll be left with is just how to think probabilistically. Much like the smile on the face of the Cheshire cat. Okay? So that's what we are, so that's what we are trying to go for. There's this intuition about how to think probabilistically. That's how we thought about random variables when we started. But now, to really understand what it is, we'll have to go to the definitions. We won't recognize the definitions, and then we will, and then it'll be consistent with our intuition. Once it's consistent with your intuition and you get that far, you can let the definitions drop because you'll now think your way through things properly. But for the moment, I'm sorry, we have to do the definitions. So let's do it. Okay, so what's a random variable again? So remember, when we are thinking when we are doing probability theory, we have a sample space omega. And we have these sample points, little omega inside it. We have various sample points. Each of them has a probability. So what's a random variable? It's a function. So let's say it's a function from this sample space to the reals. So you assign to each sample point a real number. Okay? So let's try to make sense of it. So suppose that you were flipping a coin, a coin many, many times. And suppose your sample point looked like this. Suppose that this sample point looked like tails, tails, heads, tails, heads, heads, tails, 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 heads. Okay, so that's the sample point. By the way, can you tell whether this was humanly generated? Probably, right? Well, I tried my best to put in long runs but maybe I tried too hard. Okay, so now we want to know what's W1? Okay. So remember what you do. So our probabilistic experiment is this. Well, what we do is we pick out a sample point at random according to our probability distribution. Right? It has a certain probability, so we picked it out. Maybe this is the one that came up. So it was tails, tails, heads, tails, heads, heads, tails, 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 etc. Head. So now we want to know what was the waiting time for the first heads? What was it? 3, right? How do you know it was 3? Because you had to wait that was the heads, right? Okay, so what was W2? It was 5. What was W3? It was 6. Okay, so now say that you did this experiment again and you got this other sample point, this one, which was heads, tails, heads, tails, heads, tails, heads. Okay, so now this time, what was W1? What was W2? Okay, so that's why our random variable is a function which maps our sample space to the reals. In this case, it's actually an integer random variable. So in this case, we are talking about an integer random variable, which means that we are mapping to the integers. Okay. Usually, we'll talk about discrete random variables, which means that what we are mapping to is either a finite set or it's a countable set. You know, it's like the integers or the real numbers, or the natural numbers or the rational numbers. So it's going to be sort of a discrete set. Yeah? Okay, so all right, so let's do one last example and then. Okay, so this last example is the following. So there's a so there's a secretary who's trying to stuff envelopes. There are 20 envelopes, 20 letters. The window is open. Everything blows off the table. Everything gets the order gets all messed up. This was the day that the Giants were playing their last game. He had to rush out. He didn't have time to sort of sit there and figure out which one went into which envelope. So he just stuffed them at random, hoping that everybody would get their right letters. Okay. So the question is, how many people actually received the letter that was addressed to them? Okay. So you have 20 letters, 20 envelopes, and let X be the number that received the correct letter. Okay. And you want to know what's the chance that X is equal to 0, 1, 2, up to 20. Right? So X is either 0 or 1 or 2 all the way up to 20, and you want to know what's the probability of each. Okay. So how do you figure this out? Well, let's actually do it in the case that there were only 3 envelopes and 3 letters. And let's say letter 1 was supposed to go into the first envelope, and letter 2 in the second one, letter 3 in the third one. And now, what this person did was he sort of, in the first envelope, he put a random one of these, and in the second one, a random one of what's left, and so on. So what he did was he just took a random permutation of 1, 2, 3, put them in random order. So now, how many letters went into the right envelope? Well, it was either 3 or 2. Sorry, it's either 3 or 1 or 0. Right? There's no way of getting 2 in the right envelopes without getting the third one also in the right envelope. right? Because if you got 2 of them right, the last one automatically fits into the right one. Okay, so you can see, well, these are the sample points, right? Given the sample point, you can figure out what the random variable is. The random variable is how many were in the right envelope. So that's x. Right? So now you can ask, what's the probability x equal to 3? There were 6 ways, right? So it's 1 over 6. By the way, did you figure out that when you say x equal to 1, this is a set? Right? It's a subset of the sample space. Right? So when we said, what's the probability x equal to 3, we were saying, this is the subset of the sample space. It's all those sample points where such that x equal to 3. Okay, so let me repeat what I said earlier. You know, part of the trick in probability theory is you don't look down too often, right? You know, if you're at a great height and you want to walk across, you just don't look down too often because, you know, you'll sort of feel dizzy and it's not going to be good. So what do I mean by don't look down too often? You know, so there's an intuitive notion of what a random variable is. So as far as possible, stay with it, right? But make sure that you also at some point when you're in a comfortable place, make sure you can look down and you don't fall off. So make sure that you understand what it means. So your random variable is a function from sample space 2 integers here, right? So for each sample point, you can tell what the value of that integer is. Now if you say x equal to 0, x equal to 0 is what event? Right? If you've told me x equal to 0, what you've told me is either this happened or this happened. Right? So it's a subset of the sample space. So it's an event. Right? Okay. And so when you ask what's the probability x equal to 1, you're asking what's the probability you either got this permutation or this permutation. Each of these happened with probability 1/6, so that the probability x equal to 0 is 1/3. This was 1/2, right? Oops. What am I doing? Sorry, this is a disaster. Okay. You know, in terms of you know, you can also talk about the probability distribution of x, because, you know, as we said, you know, if this is your sample space, x equal to a1, x equal to a2, x equal to a3, these are all events. They have probabilities. You can sort of draw them like this as a bar diagram, and that's called the distribution of this random variable. Okay, so when you think about these things, make sure that you keep in mind the intuitive definition, you know, the intuitive notion of random variable, and then that you can actually understand the actual formal aspects as well.